So now we're going to learn an application of an exponential function, and we're going to first look at it by looking at Newton's law of cooling. So Newton's law of cooling says that if you take an object that's warm, right, warmer than its environment, like a hot cup of coffee, and you stick it in your refrigerator, the coffee will start to cool down because it's in the fridge, but it can never get colder than the temperature that the refrigerator is set at. Similarly, if you leave a cup of coffee outside on a cold day, it's never going to drop below what the temperature of the environment is. So T naught, sometimes we'll see in formulas, just means the temperature at time zero. That's the initial temp that the coffee started at, or whatever object we're talking about. The temperature has to be cooler than the environment for the law of cooling to apply. And the temperature at any time t can be modeled by modeling the positive temperature difference. So what is the difference between the current temperature of the coffee and its environment? And then you add the temperature of the environment back in. So if we rearrange this and subtract TS from both sides, we can see that the model the calculator is going to give us is going to produce this. It's going to say, here's the temperature now minus the temperature of the environment. So the model on its own is not helpful in determining the current temperature of the coffee, but we can adjust for that when we go to answer some questions. So the positive temperature difference means that the Y value of the actual temperatures that you measure is going to have to be adjusted before we can plug it in the calculator. So we have a hot cup of coffee, it's a cold day, and you accidentally leave it outside. The coffee was 160 degrees Fahrenheit at time zero, and now the temperature outside is 37 degrees. The following data set are actual temperatures after sitting the coffee outside for X minutes. So the little t time, this is measured every 5 minutes, and this is the actual temperature of the coffee. So to build our model, just like we always do, we're going to put the X values into list 1. However, because our model is the temperature difference, we have to take all of our t values and subtract 37 to plug those into L2. So let me show you what we mean here. So in my L1, I'm just going to enter the times. So 0, 5, 10, 15, 20, 25, and 30. Then in L2, I'm going to enter 160 minus 37 because I want to know what the difference is between the current temperature of the coffee and its environment. So we get 123. Then we'll say 138 minus 37. That gives us 101. 120 minus 37. 104 minus 37. 91 minus 37, 81 minus 37, and 74 minus 37. So now I have the adjusted Y values. Now we can go to Stat, Calculate, and we want to go to Exponential Regression, and we're going to say L1, comma L2, and we're going to send the model to Y1. So vars, yvars, function, Y1. So here's our model. I'm going to write this down. I'm going to round about 3 decimal places. So the positive temperature difference as a function of time is 123.374 times 0.960 raised to the t. So this is just the positive temperature difference. If we actually want to know what the time at any given time t is, we need to take this model and add back the temperature of the environment. So now, if we go into our y equals, there's the model. So if I just scroll down to the bottom of the function, I can just manually type in plus 37. And we want to know what the temperature is after the coffee's been outside for 40 minutes. So now I'm going to put 40 minutes into my Y2 and graph. So we're not seeing our Y equals 40, so let's go to our window. So I'm going to set the X scale to 1 hour. The Y scale is starting at 50 to 93, so I'm going to go to Zoom Fit and adjust the Y scale. And remember, X is the only thing you really want to adjust manually. You always want to let the calculator auto adjust Y for you because it'll find it nice. All right, so the line is way down here at the bottom. And I'm sorry, I'm not figuring out when the coffee equals 40. Some of you are probably thinking I'm a crazy person. If we set this equal to 40, we're trying to solve for when the coffee's 40 degrees. That's not what we want to do. We want to find out what the temperature of the coffee is at 40 minutes. So all we have to do is plug 40 into our new function. So once this graphs, I can just go to second, calculate, and type in 40 minutes. So the coffee is 61.24 degrees, because this said round to 2 decimal places. Your other option would be if you didn't adjust the model. Let's say you didn't go in and manually add the 37. Well, if you just plugged 40 into the positive temperature difference, you would have gotten 24.24 degrees. That's just saying this is how much warmer the coffee still is from the temperature of the refrigerator. So then you would have to manually add back in the 37 degrees, and this does in fact give you 61.24. So I just personally think it's easier to adjust the Y1, especially if I'm going to answer numerous questions about the function. So it says, when will the coffee cool to 40 degrees Fahrenheit? So I just got a little bit ahead of myself. So now I want to go in and leave the original function alone, and now I want to set this equal to 40. And I saw from just now when I tried to intersect the lines that an hour wasn't quite long enough, so I'm going to go back into my window and I'm going to take this out to 120 minutes. Let's just go 2 hours out, and then I'm going to Zoom Fit again because I want the calculator to auto fit the Y scale for me. And this one we're going to round to the nearest minute. So there's our line. So we're going to go to second, calculate, intersect. It's going to grab Y1, it's grabbing Y2, and then guess. And it says 91.3 minutes, so we want to round to the nearest minute. So little t is about 91 minutes it takes it to cool to 40 degrees. So it took 91 minutes for the temperature to get just 3 degrees above the temperature of the fridge. So one of the things you can see about the curve is that the temperature starts cooling very, very quickly initially, but then it takes a long time for it to reach the actual temperature of the environment. So then C says, well, what is the SSE, the AE, and the correlation coefficient for the model? So to get the SSE, we're going to go back into our list, edit, and the next thing we want to do is we want to get the errors. So down here on L3, I'm going to go to vars function Y1. Oops. Something weird happened there. Let's leave that alone. It wasn't supposed to do that. Second quit. Quit. There we go. Let's go back to stat, edit, list. Let's try this again. All right. Now I want to go to vars, yvars, function, y1. There we go. And I'm going to plug my L1 values in. So I'm just going to show you how to do this another way. You could do this from the home screen like we did before. So there's all of the predicted values. Then in list 4, I'm going to say take my actual values, y2, and subtract my predicted values from L3. And then in L5, I'm going to square all those errors, so L4 squared. So now if we quit, back out to the main screen, and we go to second stat math, there's sum, and I want to sum up everything on L5. You could also sum L4 squared. I just like to do it step by step when I'm doing it. So my SSE is right here. It's very big. All right, I'm going to check that list again. These numbers feel way too big. Oh, I know why the numbers felt funky. When we go into L1, we need to remove our 37 that we put in because the calculator is adding 37 to all the Y values. So I actually need to go in here and delete the 37. There we go. So it was adding 37 to every number, and that's why that sum of squares was just enormous. So now I'll hit enter, and I'm going to go back to my list and recalculate these again. So if we go, yeah, because you can see here, look how far off. Everything was off because there was an extra 37 being added. So if we go back to L3, clear, and now I go to vars, y1, L1, see, I get much more reasonable values. So now I'm going to go back to L4, clear, actual minus predicted, and then for my L5, clear, I'm going to square all my errors. There we go. This is much more reasonable. So now we'll quit, and we'll go to stat, second stat, math, sum, and we'll sum up L5. There we go. This is much better. So we're going to go to 2 decimal places. So the sum of the squared errors is 2.20 degrees Fahrenheit squared because it's the sum or the squared errors. So you have to square the units. Then the average error is going to be our 2.2 divided by the number of data points. We had 1, 2, 3, 4, 5, 6, 7 data points. Take the square root of that, and we get 0.56 degrees Fahrenheit. To get our correlation coefficient, well, we just need to pull the model back up. So I still have it on my home screen. You could go back into stat, xreg, and pull it back up. But we can see here that our R value is negative 0.999967. So I like to just go past the first 9 because we don't ever want to round this to 1. And so what we can say here is there is a very strong negative relationship between the time the coffee's in the fridge and the temperature of the coffee. And that makes sense because as the temperature of the coffee stays in the fridge longer, it's going to drop.